Hello, everyone. Welcome back. This is Digital Computer System Architecture, Lecture 4, Part 5, Control Hazards. So we talk about how to solve the data hazard by using data forwarding. Well, we know data forwarding cannot solve all of those problems. So let's see, then control hazard, how can we solve it? Actually, control hazard is the most harmful, one of the most harmful hazards, okay? Why? Because it makes you potentially fetch the wrong instructions. So whatever you did probably is useless, right? For instance, you have this BQ branch if R2 equals 36, sorry, branch if R1 equals R2, then we branch to 36. It's here, okay? So the PC clearly, once you're executing this instruction, the PC is pointing to 14, but actually you want to jump to 36. So that's a problem. The control hazards can happen in quite a while. How do you do with the 3 instructions in between, right? What do you commit? How to do with it? So branch stall is a lot. For example, if CPI equals to 1, 30% of branches start 3 cycles, your new CPI would be 1.9 because 1 plus 0.3 multiplied 3, right? So 1.9. 2-part solutions. We determine branch taken or not taken sooner and compute taken instruction addresses earlier. For instance, the taken instruction address is 36. So we know it's either PC equals to 14 or 36. Right? MIPS use branch tests. So you calculate the branch instruction, like BEQ. We calculate the EQ first and then use that to calculate to specify the branch instruction. So the penalty of branch instruction is lower. So that we can move the zero test to instruction decoding of register or register file stage. Either to calculate a new PC also instruction decoding. Then in this case, we decide the test earlier, like branch test earlier. So we don't wait until execution or memory access, and then we decide where we go, right? So this saves a lot of clock cycle penalties. Putting them back to together into the pipeline. So if you remember, do we have that? Let's see. Okay. So we have this here. We use the multiplexer, the PC equals to 0 or not to put it in memory address. Okay. Access. Let me stop. Okay. So see here we have put the old design and the new design here. Clearly, you can see they do the branching, like deciding the next PC earlier in the instruction decoding versus in the memory access. So this saves quite a bit of instruction cycles. We say 1, 2, 3. So this saves from 1 penalty to 4 penalty to 1 penalty. So it's like saving 3 cycles, right? For branch has alternatives, so we can stall until branch direction is clear, or we predict branch is taken or not taken. We're gonna have a lot of lectures about this. Basically, we execute the successive instructions if we predict it's taken. Then we go to the taken, we'll assume it's taken. So we go ahead, execute that taken instruction. If it's not, then we go ahead and execute the not taken case. Okay. If our prediction is wrong, then we squash the instruction in the pipeline. All right. The advantage of late pipeline stages is that we can easily calculate the branch taken or not taken average, and then choose that specific one as the static taken or not taken. When we, if it is taken, typically we cannot calculate branch target address in MIPS. So this still incurs 1 cycle penalty. Some machines has the branch taken known before outcome, so then you can easily do that, right? Or we can delay the branch. So how we do delay the branch is the same as our exercise in last part. You basically define branch to be taken place after a following instruction, right? 1 slot delay allows proper decision and branch target address in 5-stage pipeline. For instance, if the branch is here, I will execute the, no matter what, has to be added stuff later. So we have the delay here. Okay, sorry, this I is wrong. And then from branch target, first of all, from before branch, second from branch target. From branch target, assuming we have this subtraction here, right? We delay it to here. So when you are executing the branch, you always have some instruction that always has to be being executed, right? For the third one is you have the delay here, delay slot here. Then we use the subtraction, which means this instruction, no matter what, has to be executed, right? We put this fill in the delay slot, right? Taking all of them together is that we use some, no matter what, has to be executed instruction to occupy the delay slot, right? The delay slot is always being occupied, but it can be occupied instruction before the branch or from the branch target or from fall through, right? So clearly A is the best choice because it fills the delay slot and also using the instruction that always has to be executed. Well, in B, the subtraction instruction might need to be copied. This increases the instruction count, right? In B and C, must be okay to execute the sub when branch fails, right? Like your instruction failed, branch failed, then you still have to execute the instruction. Delayed branching is actually very effective for single instruction delay. It fills about 60% of the branch delay slots. About 80% of instruction executed in the branch delay slot is useful in computation. About 50 of them together is like 50 useful, right? Delay branch downsets as the processor goes to deeper pipeline and multi-issue, the branch delay grows and need more than 1 delay slot. Then we might not be able to find so many delaying instructions to fill in the delay slots. Delayed branching has lost popularity comparing to more expensive but more flexible dynamic approaches, which I will talk about later. Growth in available transistors has made dynamic branch prediction approaches relatively cheaper. Evaluating the branch alternative, pipelining speed up equals pipeline depth divided by 1 plus branch frequency multiply branch penalty. This is like the pipeline stall, right? Assuming 4% unconditional branch, 6% conditional branch taken, and 10% unconditional branch, conditional branch taken, right? This untaken is taken. So we can say stop hype branch penalty 3, CPI 1.6, speed up versus M pipeline is 3.1, speed up versus stall is 1.0. Branch predictor taken, branch penalty is 1, CPI is 1.2. Speed up over ARM pipeline is a 4.2. Speed up over star is also better, 1.33. Predict not taken, like a static prediction. Branch penalty is 1, then CPI is 1.114. The speed up over ARM pipeline is 4.4. And then for delayed branch, like using the deleting instruction to fill in the branch, you can say the speed up is the best, 4.5, and speed up over the star based without, like basically without filling in the branch, filling in the delay slots is 1.45. Okay. So this pretty much gives you a hint about what is branch prediction, right?